Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Afika Izzati binti Tanjid. My matrix number is 190868. So today I would like to tell about Sigma Delta Analog to Digital Converter implementation on Field Programmable Gate Array, which is FPGA board. So for the introduction, as what we know, ADC are very crucial components in nowadays because we needed it in communication, signal processing, and also biomedical field. Other than that, for signal processing, ADC is very low power consumption, but it has high conversion efficiency to convert analog signal to digital signal. As what we know, the real world is mainly on analog domain, while the transmission of the signal is digital domain. That's why we need ADC in our life. So, how we convert it is by having electrical signal that is collected from the sensor that is in analog domain, and then it will be translated into a digital form. So the objective of this project is to design, simulate, and implement Sigma Delta ADC on FPGA. Second, to analyze Sigma Delta for conversion time improvement, and third is to propose Sigma Delta structure to improve performance. So for the literature review, why I use FPGA? Because it can be programmed or reprogrammed as what we wanted it to be. Then for ADC implementation on FPGA, we no longer need the additional chip. Like we only need minimal connection for passive component to the FPGA. So the passive component will be discussed later. So this is the difference between SAR and Sigma Delta ADC. Why I use Sigma Delta ADC? Because even though it is slower, the conversion rate is lower, but it have higher bit resolution, which we can have starting from 8-bit to 32-bit, and then we use minimal external connection. So Sigma Delta ADC is known as oversampling ADC because it oversamples the Nyquist sampling theorem by twice. So this is the Sigma Delta modulator. This circuit decreases the complexity of analog interface by using digital logic. So as what we can see, there are different integrator, comparator, latch, and DAC. The integrator is built up by RC, which is resistor and capacitor, and then the comparator is inside the FPGA as well as latch and DAC. And then the circuit will only produce one bit stream. That's why Sigma Delta have longer conversion rate because it only produces one bit at one time. So the software used is PSIM, Quartus, Altera Model SIM. Hardware we use DE1 FPGA board, resistor, capacitor, and jumper. So this is the simulation. As we can see, this is the rising edge sampling. This is the LVDS comparator. This is the integrator. This is the rising edge decimation, and this is digital out. So how to determine the resistor is by using the formula right here. The N is number of bit, Fs is sampling frequency, and C is capacitor. We use 27 MHz frequency sampling because it is available on the FPGA board. So the resistor is 9.48 kilo ohm. It is approximately to 10, and Sigma Delta is not sensitive towards the value of tolerance on resistor. That's why we use 10 kilo ohm. This is the setup. The analog is we use 10 kilohertz, and for LVDS, for the comparator, we use 1 volt in the PSIM. However, in real life, we can use up until 3 volt. But PSIM only limit until 1 volt. The clock is 27 megahertz. Digital out is 8 bits. The resistor is 9.48K, and the capacitor is 1 nano. So this is the result. This is the output of 8-bit, and this is and log input of 10 kilo. When we zoom in, we can see the conversion time is 9.48 microseconds. It is calculated as the equation right on the right. So this is the result. As we can see, we only need external component, which is capacitor and resistor, and I/O pin required on FPGA is 2 LVDS pins. So as the conclusion, we can know that the sigma delta ADC can be implemented on FPGA with external component needed. The higher the bit resolution, the higher the conversion time, because sigma delta only produce one bit at one time. So that's why it will take a longer time for higher conversion. But when the both edge clock is sampled, the conversion time will become faster and more data can be converted. Recommendation, I would like to suggest that we use decimation function with an integrated digital filter because it is specified inside the FPGA. But for this experiment, I only use uniform decimation only. And then if we make dual signal sigma delta ADC, we can make use both of rising and falling edge to sample data. And then the faster the conversion time, the more data that we can be convert. I think that's all from me. Thank you.